All right, chapter 9. We're going to be looking at probability in chapter 9. So 9.1 is sort of our introduction to that concept. So we're going to see more definitions and stuff in this section. And to start out with, that's exactly what I'm going to start out with, a few definitions. First, experiment. So while a science experiment is certainly an experiment, these type of experiments are more broadly defined. It's any activity whose results can be observed and recorded. So an experiment in your classroom someday might be that you're going to try a new lesson in a different way than you ever taught it before, and that is an experiment, right? And the recorded results would probably be the student's level of understanding either from a qualitative standpoint, right, you're observing, or from a quantitative standpoint, what are the grades that they get? An outcome. An outcome are the possible results, each possible result from an experiment. Right, the things that can happen and take place. The sample space is the collection of all those outcomes. So it's like a grouping or a listing of every possible outcome that could take place. So you might sort of imagine like if you were giving kids a test and you have, I don't know if they make them anymore because I don't see the need for them, but they used to have these keys that teachers could say, and they would say, oh, look, there was 15 questions, and if they missed one, this is their grade, and if they missed two, this is their grade, and if they missed three, this is their grade. They had like a key kind of thing like that. That collection would be a sample space for that particular, test or assignment or whatever. And an event is any subset of the sample space. So maybe it's the event of the students who got an A, or the event of the students who passed, or maybe it's the event of the students that didn't pass, right? So some collection of smaller a subset or a smaller collection of the sample space. Okay, a lot of the ones that we're going to be looking at in this section are going to be numerical examples because of the things we're doing with them. So obviously the examples that I just gave you with grades are numerical examples. But we're going to be looking at things that we can calculate, just like simply calculate, not have an actual experiment to take place. And so what we're going to be looking at is going to be looking at mostly gaming kind of things. So rolling dice, flipping coins, things like that. Things that we can count easily what's going on. So as we move forward with this, keep that in mind, is that everything I'm describing is not only applied to that, that's just the way that the section is geared in terms of the questions they ask, mostly geared toward gaming situations. Theorem 9.1 is called the law of large numbers. A mathematician named Bernoulli is credited with this theorem, so it's often called Bernoulli's theorem as well. And it says if an experiment is repeated a large number of times, then its probability will approach a fixed number. Right, so if we repeatedly flip the coin 10,000, 100,000, 1,000,000 times, it's going to approach the probability of having 50% of the time you get heads and 50% of the time you get tails. Right? It's got to be a large number of times that you repeat the experiment. If I give the same test to 500 students, 1,000 students, 15,000 students, right, a large number of students, there's got to be sort of an average of what is expected to happen over a time frame. That's how standardized tests get their scaling, right? That hundreds of thousands of people, millions of people maybe take this test and they say, a third grader should score right here based on our results. Probability is calculated as the number of ways that you can have an event happen, that's the N of A, divided by the number of items in the sample space. So at this point, I think I need to create an example so you can see how this works. So we're going to consider rolling a die. And this is just your standard six-sided die. So the sample space, S, means all the outcomes that can occur. So we have 1, 2, 3, 4, 5, or 6. There are 6 different outcomes that can occur when we roll the die. Okay? And if we want to let A be the event that we get, say, a even number, how many even numbers are there? Well, there's the 2, the 4, and the 6. So if I want to calculate, sorry, I don't really have a lot of space here. Let me move down at least for the next step down here. If I want to calculate the probability of rolling an even, What I do is I write the number of ways that I can roll an even, that's 3, on top. And I write the number of ways that anything can happen, that's 6 on bottom. And if we reduce, we have a 1/2 probability of rolling an even, which you probably intuitively knew if I just asked you from the outset of this particular example, right? You knew there's half the numbers are even, half of them are odd. It should be a 50-50 shot, right? But we can do this for less intuitive calculations as well, right, when we have a different scenario. All right, now that I'm all over my screen, the one that I marked over, we're going to read that one. Mutually exclusive is events A and B that have no elements in common. So with the one that I've given, what would be a mutually exclusive event to rolling an even? Has nothing in common with it. Rolling an odd. Those would be mutually exclusive events. Now those two events happen to cover all options, right? You could also talk about the mutually exclusive event of rolling a 1 or rolling a 2. They also have nothing in common. I can't do both at the same time. I can't roll a 1 and a 2, right, if I've got one die. So it doesn't have to cover everything in order for them to be mutually exclusive. They just have to have nothing in common.
What is the little upside down?
Oh, yeah, so depending on what you've seen before, you might not see this, have seen these symbols. Thank you for asking. All right, so this symbol is a symbol for intersection. It comes up earlier in our textbook, like in earlier chapters of our textbook. It also comes up in our contemporary math textbook. So if you still have those courses to take, you'll see it again. Intersection just means what they share or have in common. And then this symbol right here at the end also comes up in both of those textbooks. This symbol right here is the empty set symbol. So it's just a collection or a representation of a collection that has nothing in it. Right, so it represents a set of nothing, nothing in common. So we're not going to see this notation used a lot in this chapter, but it does come up in the definition. Okay? Anything else on the slide that I didn't think to address? Okay. A couple more theorems. Actually, we have several more on this page. 9.2 says if you have an event A, and S is your sample space, then the probability of the event is between 0 and 1. And it probably helps you, or will help you to think about probabilities as a representative, as a decimal form of a percent. So the corresponding percentage, if we were thinking percentage here, would be saying that this is between 0% and 100%. So we talked when we looked in chapter 7 about percentages and how you can have more than 100%, but there's a specific context in which that makes sense, right? But you can't have more than 100% in the situation of probability, right? Because 0 means it's never going to happen, 0% chance. 1 or 100% means it's guaranteed to happen, right? 100% chance none of us are in this room at 3 o'clock. Guaranteed going to happen, right? None of us are going to be here. Empty room. Yeah, amen. Spring break, right? Okay. Or you could say it's a 0% chance that any of us are going to be here. We could say it from the other side too, right? But there's no way to have less than 0 or more than 100. It has to be between those. So it's less than 0, more than 1 when we're talking about the decimal form, the probabilities. Theorem 9.3 says the probability of an event is equal to the sum of the probabilities of the disjoint outcomes making up the event. There's a lot of fluffy language, florally language basically for saying that if I wanted to find the probability of, say, we've got our 6-sided die example again, the probability of rolling an even, I could find the probability of rolling a 2 plus the probability of rolling a 4 plus the probability of rolling a 6. 2, 4, and 6 is how I get an even. That's how it is. So those 2, 4, and 6 are mutually exclusive events. They have nothing in common, right? Just like we looked at it before. Disjoint or mutually exclusive events. And if I were to find the probability of rolling a 2, well, there's 1 2 out of 6 numbers. There's 1 4 out of 6 numbers. And there's 1 6 out of 6 numbers. And what we learned back in chapter 6 with fractions, says that since the denominators match, we could add our numerators, and this would be the probability of 1/2, just like we found when we looked at it from a collective standpoint on the previous slide. So if it's easier, and it might be sometimes to break things apart instead of to think of them as a whole, you can break things apart to calculate these probabilities. Okay, a couple more. Theorem 9.4 goes back to that mutually exclusive idea. So events that are mutually exclusive, remember, means having nothing in common. If you want to find the probability of the union, okay, so this means union, another symbol. Again, we're not going to deal that much with these, but this means union. So union means collecting these things and sort of merging them together, okay? That if the events are disjoint, like we did on the last problem, then we can just add each of the individual pieces together and we can create that. It has to be disjoint for that to work, okay? So what things won't work? Well, let's say, for instance, instead of trying to find the probability of even numbers, you wanted to find the probability that it was even or prime. Okay, the collection is even or prime, not just even, but we've kind of merged two things together, the evens and the primes. Well, the problem is that they overlap. Do you know any even numbers that are also prime? 2. 2 is even. You know it's even. Prime numbers, if you'll remember, means that they are only divisible by themselves in 1. 2 is the only even prime number. But because this overlaps, we can't simply count the number of evens, there's 3, and count the number of primes, there's 3, and say that the probability of this happening is 6 out of 6. Guaranteed when I roll that die, I'm going to get a prime number or an even. It's not true. Because the number 1 is not prime, and it's not even. And the number 5, I'm sorry, not the front of 5, the number, actually, is that the only one? It is, it's the only one. So there's a possibility of that not happening. So when things don't actually have the ability to be separated into two distinct things that are completely different, this theorem won't hold. That's why that mutually exclusive clarification is in there. 9.5 talks about complements. Again, a notation that you see in other classes. This right here, when I see this line on top of it, means that something is not in A. So if A is all the collection of evens, then not in A would be the collection of odds that we talked about before. Okay? Evens and odds are a really good example for justifying how this works. So this says that if I had the probability of the evens plus the probability of the not evens, namely the odds, that would equal 100% or a 1 probability, the entire sample space. It would include everything. And if I take that formula and I just adjust it by shifting, the terms to the other side, I get the other two equations. The other two equations aren't any different. They're just a shift of algebra. So if I take the probability of the A complement, I can move it to the right-hand side, or I can take the probability of A and move it to the right-hand side. Sometimes it's a little bit shortcut, at least one step, in terms of finding these probabilities by having the alternate formulas available. Okay, the next thing is just a table where all of these theorems are going to be merged together. So it's like a listing. Okay, so I've explained all of them in detail. Now we're just going to do a list that has them all in there. So the first one is the probability of the empty space, right? That means it's an impossible event. Right, so if I'm rolling a single-sided die, the probability of rolling a 7 is 0. There's no 7 on the sides of the die. That is an impossible event. Probability of S, that's the entire sample space. That's 1. Right, so what's the probability when I roll the die that I'm going to get a number that's between 0 and 7? Well, strictly between 0 and 7. 1. Guaranteed going to happen, right? All other probabilities, in fact, all probabilities are between 0 and 1. That's the third one on here. All our probabilities are between 0 and 1. Number 4 is the mutually exclusive one that we talked about just a moment ago. It says if they're mutually exclusive, they have nothing in common. That's what this notation here means, nothing in common. then the probability of the union is the addition of the individual probabilities. The fifth one here is new, so let's just jot it down and then I'll come back to it. I'll explain that one in a second after you're done writing. The last one is one version of those three formulas on the last theorem, on theorem 9.5. So the probability of A complement is 1 minus the probability of A. Try not to get hung up in all the notation. The problems themselves use very little of it. Okay? When you see the numbers in play, they'll make more sense than when you see the notation, especially if you haven't seen this notation before. It's not a big deal. The one that we skipped, that I said, this one's new, I haven't actually discussed this one. It actually talks about what happens in the case that you don't have this condition right here. This condition right here creates a simpler equation, and if you don't have that condition, it's not quite as clear. So let's go back to my example with the evens and the primes. So if you have the probability of rolling an even or a prime, we talked about the fact that those overlap. So if you only calculated the probability of rolling an even, and you added to that the probability of rolling a prime, we would end up with 3 over 6 and 3 over 6. But the reason is because the number 2 was in both sets, right? Both descriptions. So what this is saying is that you need to remove the probability that they have in common, whatever's in common. So in us, actually, I'm not going to write common here. I'm going to write the probability of rolling a 2, because we already said 2 is what's in common. So if we were to calculate the overlapped part and remove it, we could still use this formula instead. So we'd have a 3 out of 6, and we'd have a 3 out of 6, but we would remove the 1 out of 6 for the number 2 that they shared in common, and we would get a 5 out of 6. And if we actually counted them, we can see that makes sense. So the number 2 is prime. That one's good. The number 3 is prime. The number 4 is even. The number 5 is prime. And the number 6 is even. So we do in fact get 5 of the 6 numbers that are in one of those two categories. And that's what that one's talking about, is just removing any double counted outcomes. Okay, so as promised, we're going to do an example. You ready for it? Okay, in order to do this example, I need a little bit of background knowledge. Some of you are going to be like, duh, this is really obvious. And others of you are going to be like, never worked with cards in my life, and so I need to know. So jot these things down if you need them, because you're going to have some examples. It's not going to be all the examples that show up, but we will have them show up from time to time. We're going to be using a standard 52 card deck. That's the standard deck it's talking about. The standard deck has 52 cards. Okay? The deck has 26 reds and 26 blacks. It's half red, half black. Okay. It has 4 suits. It has hearts and diamonds. Those are the red ones. And then it has clubs and spades. Those are the black ones. Since there are 52 cards and there are 4 suits, that means each suit has 13 cards. So there's 13 hearts, 13 diamonds, 13 clubs, and 13 spades. Okay, within each suit, so let's just pretend we're within one suit, we're in hearts. Within each suit, there is one of each of the following numbers. You have numbers that go 2 through 10. Those are the number cards. So you have a 2, a 3, a 4, all the way up to a 10 card. You have the face cards. The face cards are jacks, queens, and kings. So there's 3 face cards in each suit. And you have the ace. And depending on how the game is played, sometimes ace is considered a high card, sometimes it's a low card. If you're playing blackjack, it could be either one. And it's not considered a face card. Okay, it's not. It doesn't have a face on it. Like literally the jack, queen, kings have faces on them when you have a standard deck. Ace is not considered a face card. Okay, I think that's enough for us to do any of the problems we're going to encounter. But if there's something I say and you're like, wait a minute, how'd you get that? Ask, because I know that's not an intuitive concept depending on the gaming history you've had from a card game perspective. We play a lot of card games in our house, so it is very familiar in my home with my children, but I know that's not true for everyone. Okay, so what we're going to do is we're trying to decide if each of the events in the descriptive, curly braces are equally likely. So we're actually going to do a counting of these objects to make sure that we see how they work, because some of your questions are not just going to say, are they equally likely? They're going to say, find the probability. So we're going to find the probabilities on this, even though that's really not that's not exactly what's being asked. So it's sort of an overkill, okay? All right, so how many face cards are there? Well, how many face cards did I tell you were in each suit? 3. There's 3 face cards, Jack, Queen, and King. And there are 4 suits, hearts, diamonds, clubs, and spades. So how many face cards total are there? 12. There are 12 of them. So this one is and actually I'll just write them underneath. I really need to change this slide so there's more space. There's 12 face cards out of a total of how many cards? 52. So there are 12 out of 52 are face cards. That's the probability of a face card. So how many cards are not face cards then? Renzi said it. 40. 40 actually. Yeah, 40. That's okay. There are 40 that are not face cards. 12 are, 40 aren't. 40 out of 52 are not face cards. So is it equally likely when you select a card at random that you will select a face card and not a face card? No, because there's more cards that are not face cards, right? Yeah, so this is not equally likely. All right, how about clubs? How many clubs are there?
13.
There are 13. Out of how many cards? 52. How many diamonds are there?
13.
Out of?
52.
Okay, how many hearts are there?
13.
Out of 52. And the last one, spades?
13.
Is it equally likely that you select any one of these categories of cards? Yes. This one is equally likely. All right, black and red. How many black cards are there?
26.
26 out of?
52.
Okay, and how many red cards are there?
26.
Out of?
52.
Are these equally likely? Yes, they are equally likely. All right, last one. How many kings are there?
4.
There are 4. There's a king in each of our 4 suits. Yeah? Okay, so there's 4 kings out of 52. How many queens are there? 4 out of 52. Jacks?
4.
Out of the 52. How many aces? Out of the 52. How many even cards? Okay, so Addie said 5. Do you know where she got 5 from? Yeah, good. So that's a good place to start. So 2, 4, 6, 8, and 10. So there's 5 of each suit.
So 20.
So there's 20. Yeah, so we'll get there. Yeah, there's 20 even cards out of 52. How many odd cards are there? There's 4 of each suit because we don't have yeah. So we have 3, 5, 7, and 9. There's only 4, right? There's 4 of them. And there's 4 suits, so there's 16 odd cards. Are these events equally likely? No. They are not equally likely. Okay, so again, did you actually have to write out all those probabilities to answer these questions? Not necessarily. But you could be asked a slightly different question where they did just ask you find the probabilities of these things. So I wanted to make sure you'd seen us do that with this problem. All right, we're going to do the next one as a Civ class. All right, a Civ class is composed of 21 men, 34 women. 22 ed majors, 13 religion majors, 12 science majors, 5 English majors, and 3 math majors. We do need the next assumption to be holding true, otherwise we won't be able to do this problem. Assume no one has a double major. Otherwise this is not going to work. Assume no one has a double major. Okay. If a single student is chosen at random, what is the probability that a student is, and then we've got some categories. The first one is female. How would I find the probability that the student that I've selected at random is female?
21 plus 34.
Okay, so you're going to start with adding these. What is that going to give you? What value?
55.
And what does that tell you? 55 what?
Students.
Right, 55 is the total number of students in the class. So how do I figure out the probability that the student is female?
34 over 55.
34 over 55. Does that make sense? Okay, we always want to look and see if we can reduce the fraction. We've spent some time doing that recently. Can this fraction be reduced? No. No, we can't, right? No. Don't overthink this. But some of them will, some of them won't. This one just doesn't. It doesn't reduce. Okay. How about a science major? All right, so the science was, where is it? 12, there it was. Sorry, I kept reading over it. 12 out of 55. Can that one reduce? Yeah, no. Which one is it? Yes or no? No, it doesn't. Yeah, it's a no. It does not reduce. All right, the next ones are a little bit more involved. This one says, C, says an English major or a religion major. What do we have to do? All right, so we find the English, that's 5, and we find the religion, that's 13, and we add them. You're right, so 13 and 5 would be 18 out of 55. There's 18 out of 55 of them are one of those categories. The last one says neither a math major nor a science major. How do we do that?
You add them and subtract them.
You can. So that's one way to do it. So we could add the math and the science, or we could add the others that are not the math and the science. Your choice. Either way, you'll get the same thing. So since Kate mentioned that way first, we're going to do it that way. The math is 3. Oh, I was wanting to use a different color. Let's try that again. The math is 3, and the science is 12. So 3 and 12 are what? 15. So how many would I have that are not in that 15 now? Somebody about to say it? How many people are there total? 55. Take away the 15, I have 40. So there are 40 out of 55, and if you add up the others, it'll be 40 as well. Does this one reduce? Lo and behold, it does. What does it divide by? Yeah, top and bottom by 5. So what's 40 divided by 5? 8. And 55 divided by 5? 11. So it's 8 out of 11. Okay. The questions that remain, I think all of them, at least the next 3, the next 3 anyway, are all type C questions, okay? So, first one, a student claims that if a fair coin is tossed and comes up heads 5 times in a row, then according to the law of large numbers, the probability of tails on the next toss is greater than the probability of heads. What is your reply? Well, he's wrong. Thank you, Kate, that's true.
Because in this case, it's just half, like, it's equal probability, so it might be greater. Just
Okay.
because he's tossed it 5 times in a row.
Okay,
It doesn't
so
change how many times he tossed it, doesn't change the probabilities.
yes, you've hit the nail on the head for the biggest part of this problem, is that in a single toss, the probability is always 0.5. It's always 0.5, regardless of previous tosses. There's something else that we probably want to address with him based on what his description is. Any idea what it might be? Something about the theorem. What about the theorem? Yeah. 5 is not a large number. At least in most contexts. If you have 5 children under 5, it's probably a large number, but in most contexts, 5 is not a large number. So this theorem is completely irrelevant anyway, right? It doesn't even make sense to talk about it. Now, it's not relevant already because the theorem doesn't talk about what happens in a single toss, right? 150,000 people take an exam, the average score is a 50. It doesn't mean the next person coming in is going to get a 50, correct? Right? That doesn't work that way. So that's not really helpful regardless. But even if we were talking about something that worked from the standpoint of a generality, it wouldn't work here because this is not a large number. So there's a couple of problems with his thoughts. Now let's take a look at another game. It's a spinner game. The following spinner is spun 100 times. Joe claims the number 4 will occur most often because it has the greatest area of space on the spinner. What would you tell Joe about his conjecture? Conjecture means what he thinks is going to happen. And then what is the probability that 4 will occur on a spin? You have to first decide, is his conjecture true or is it false? Does it make sense? Does it not make sense? And why?
It's false.
It is false. Do you have an inkling of why?
Because it doesn't, the spinner, it's not as big as the space. And so even if the space is bigger, it won't reach it.
Okay, so what I hear you saying, Addie, is that there's something about the space that doesn't matter.
Yeah.
Can somebody help her on describing why?
The spinner is like attached at like where
Mhm.
the intersections meet, and each number has like the angle makes it a 90-degree angle, and so the space doesn't really matter. It's where the angle between.
Okay, so let me start with, these two answers put together are going to be really good for us. So the area isn't important to the spinner. And I don't mean the person spinning, I mean the spinner that's in the middle, the object, right? It isn't important to the spinner. The spinner goes through, I'm not sure that's the best word, but we'll go with it anyway, goes through the angles and all 4 outcomes, right, the outcomes 1 through 4, are, and you even said, I think you said right angle or 90-degree angles. We could just simply also say they're the same angle measure. They're the same, right? Every angle that this spinner spins through is exactly the same measure as the previous angles. So what is the probability of spinning a 4? It's 1/4, because there are 4 equal angles there. So now we're going to take this picture and we're going to change the context. Instead of a spinner, it's a dartboard. How does that change your response to Joe?
Well, in that context, the 4 would
Yeah, there's more space in which your dart can land, right?
It'd be a lot harder to hit the one.
Sure, because there's less of it, which is exactly how dartboards are created, right? You got the bullseye, and then you got these rings outwards of them, and it's harder to hit the very tiny piece in the middle than it is the outer piece. They don't usually look like our spinner here, of course, but yeah. So the probability of 4 here is greater because the dart is more likely to hit a larger area than a smaller one. So he's correct if we use this one instead. All right, my last example is actually with a little bit of data. We have seen a data example like this before, and so we're going to do one more of them because I collected a whole bunch of data, and by golly, I'm going to use them. So this is data I collected during COVID. So during, all that time that you were shut up in your house, yeah, that's what was happening. So we've seen this before. Recall as of August 1st, 2020, the number of positive COVID cases in the state of Oklahoma up to that point had stood at 37,731. The population of the state of Oklahoma as of July 1st, 2020 was 3,956,971. I realize that those dates are not perfectly aligned, but that's the closest I could get when I created my data. So we're going to go with them as though they are aligned. They're close, right? They're only a month apart. Few people born, people died. Can't change it that much. On August 1st, what was the probability of interacting with someone who had tested positive for COVID-19 at some point? Not necessarily they were positive at that point, but you knew somebody who had had it at that point. That's kind of the picture in your mind. Like, how many of you knew somebody who had had it at that point? Kind of perspective. So what we're supposed to do is supposed to find the probability of the person having COVID. So we would need the number of people who had had COVID divided by the number of total people. So what number would go on top? The 37,731. And what number would go on bottom?
3,956,971.
Yeah, you read that perfectly. Good job. 3,956,971. And when we're dealing with real life data, oftentimes fractions are not very friendly. We want to turn them into a decimal, and that's okay. So feel free to grab your calculator to turn this into a decimal. And again, generally speaking, we're going to use 4 decimals. If they tell you to do something different, by all means, do what's being told, but we'll use 4 decimals unless we're told otherwise. So what is the decimal value for the probability of this situation? It's got to be between 0 and 1, by the way. So if you're getting something that's not between 0 and 1, we've got a problem.
What decimal place did you say you went to?
4. I wrote it at the bottom. It's kind of tiny, though.
0.0095.
Okay. Do you have confirmation of that? Somebody else got that too? I did too? Great. 0.0095. And to give you some perspective in terms of fractional value, this means 95 out of 10,000 people, because we're in the 10,000s place. We learned that back in the last section about those place values. 95 in 10,000, or that's approximately 1 out of every 1,000 people. That's what that would be approximate to. Okay, are we good? Okay, so that's the probability. That's very small. And that's not the people that are currently positive, right? It's people who've tested positive for the previous, 8 months or 4 months or whatever we've been testing for at that point. Almost 8 months, probably. We've been pretty close. Also, on August 1st, it had been reported that there had been 549 deaths and 30,282 people who had recovered. Okay, so go back and look. 37,731 had it. 549 had passed away. and 30,282 got better. What is the probability then, at that point in time, this is a split-second point in time, of interaction with someone who is currently infected and knew it? They had to know it, or the numbers don't make sense, right? They had to know it. So, well, we need the number of people who have it. Oops, I didn't mean that. That's my top. We have the probability of people who have it. So this would be the number of people who have it divided by our number of people total. Okay, well, we had 37,000 that had tested positive, 37,731. You're not interacting with the people who've passed away. So that's subtracting off that 549 because you can't interact with them. And those 30,282 are no longer contagious because they recovered and they're now well, right? So they don't count in this total either. And now we're dividing that again by our 3,956,971. So just for starters, what's that numerator give you? So that we're all on the same page. 6,900 is correct. And then we're dividing by our 3 million. And again, decimal form is fine with 4 decimal places. It should be smaller than the 95 we got before because I've got a smaller numerator. What'd you get?
0.0017.
0.0017. And again, that means 17 out of 10,000, or approximately 2 in every 1,000 people. I didn't write that right. 2 in every 10,000 people. Right? No, I did write it right. 2 in every 1,000 people. I wrote it right the first time. 2 in every 1,000 people. 2 out of every 1,000 people. No, I didn't. What did I do wrong? Oh, I wrote this first one wrong. That's the problem. This should have said 1 out of every 100 people. I apologize. Fix that one for me. 1 out of every 100 people. I got my numbers off on. I was looking at the wrong line. 1 out of every 100 people. So you had about a 1% chance that you were working or in contact with someone who had had it or currently had it. And over here, a 2 out of 1,000 people that are currently contagious, essentially, that were aware of it. All right. So I wanted you to be able to see how we kind of work with these values. And this is some data that I had. They'll give you other data that you're going to be working with in your homework. All right.